Hello, everyone. Thanks for coming. Today, we are going to talk about Apache Carbondata, an indexed columnar file format to tackle some challenges we are facing for analyzing large data sets. And the integration of Carbondata with Apache Spark has been able to enable faster interactive queries with Spark SQL. So no doubt, nowadays every company generates lots of data. And for instance, in a typical telecom companies with millions of terminals, it can easily generate millions records in a very short period of time. Now we have systems to store them. And also there are distributed processing framework available to manipulate those data and perform various analytic workload on top of them. So here are some examples from traditional BI dashboard for keeping track of a business KPIs or OLAP type of queries, batch processing over historical data, or real-time analytics over streaming data, and lastly, advanced analytics like machine learning to gain insight out of the data. But still, we are seeing some challenges when integrating with enterprise applications. In general, they still prefer or requires a very low latency on wide spectrum of query analysis. From OLAP type of queries, which involve joins and aggregations, versus detailed queries, which might fetch many columns out of wide tables. From big scan type of queries, which scan a big chunk of data out of a huge table, versus a very selective filtering queries, which involves only a small scan, as well as point queries, which is more or less like a key value lookup, which you only touch a very small portion of huge tables, which contains billions of records. So now it comes to the question of how to choose a storage engine to facilitate query processing with various different data access patterns. Over the last decade or more, there are a lot of systems and tools are flourished to address a different aspect of application needs. So here we summarized into 4 categories. First one is NoSQL database, which is like key value stores, and they are generally offer very low latency on write, and also on read for key lookup. But they generally doesn't offer standard SQL support. The second category are traditional MPP relational database, which with a shared nothing architecture, they enables very fast query processing. But they generally suffers a poor scalability issues and doesn't offer fault tolerance. The third category are search engines. With advanced text indexing techniques, they can offer fast search. But they generally could cost 3 to 4 times data expansions in size and has no SQL support. The fourth category are SQL on Hadoops with modern distributed architectures, and they offer high scalabilities, but they are slow on point queries. Here we list a couple typical systems out of either from open source or from different vendors, and you can see there are many of them. Even with so many options out there, we are still having a hard time to actually pick a system which is capable of doing all 3 different types of query processing we are listed here. Big scan queries, which require high throughput big scan of a huge table, or a fast random access with a small scan type of query, or very low latency on a multi-dimensional OLAP type of queries. So that's the motivation for us to come up with a new file format to be able to do a much better job for all three types of query patterns. So here it comes Carbondata, a unified file format, a single copy of data, trying to balance all three types of queries to fit all different data access patterns. We thought this is a pretty cool idea, and we started working on this about 2 years back. And last year, we decided to open source it, and we entered the Apache Incubator projects in June 2016. So far, we had 4 stable releases. The last release is 1.0 release, and which released about a week back with the rich feature list, and we also upgraded Spark version to version 2.1. Because we are an open source project, and we have been able to attract developers from companies outside Huawei to contribute and grow the community. Here we list a couple of them. And later last year, we started doing POCs. And after a couple of successful POC, we now have a couple in production deployment of Carbondata in Bank of Communication. It's a big bank in China. We are helping them with speeding up their point queries. And also within Huawei, for our cell phone business, analyzing cell phone data, which mainly are OLAP type queries for speeding up OLAP type queries. Hulu is an online video provider. They have done sophisticated testing on Carbon compared to other existing, and they have been trying out Carbon for their OLAP type of queries. So now you may be wondering what exactly is Carbondata. So to make it a little easier for you to understand, we're going to explain in 3 different angles. So first, we're going to start with what is Carbondata file format, how Carbondata files are structured and laid out on disk. Then we're going to move on to what forms a Carbondata table. And beyond Carbondata files, there are metadata information as well as index information we stored for query processing. Lastly, we're going to talk in great detail about how to integrate Carbondata with Apache Spark to leverage the indexes we introduced in Carbon. So if I have to use one sentence to summarize what is Carbondata, Carbondata is an indexed columnar file format. So what do we mean? So from a very high level, you can see we introduced multi-level indexes to columnar storage. From multi-dimensional B-tree index, we also support column level min-max index, as well as a column chunk level inverted index. We're going to talk in more detail in following slides. As a file format, we also support a couple very efficient encoding schemes. To name a couple, we have RLE Delta and dictionary support. For dictionary support for low cardinality columns, we also support global dictionary encoding. We will talk in more detail about some optimizations we have done with the global dictionary in later on slides. For compression, we support snappy compression. We also support adaptive data type for compression, which taking into account of a data statistic of the column to have a better compression ratio. For supported data types, we support all primitive data types and a couple nested data types like a struct and array. So now let's move on to take a closer look at how a Carbondata file is laid out. As you can see, here is a visual representation of carbon data files. A carbon data file contains a sequence of blocklets. Each blocklet is a set of rows in columnar format. So you can see each blocklet contains a column chunk for each column defined in the file. And when you define a carbon table, you actually pick a set of columns to form what we call MDK index keys. And then data, during loading, data is actually sorted along the MDK index keys and then chopped into files and stored. So at the file footer, we will have some metadata information at the file level as well as the schema of the file. Blocklet index, we're going to talk in next slides in more detail, which is a file level index, which will take advantage of MDK index we talked about. So if we take a closer look at our file level blocklet index, remember at the file footer, we store the file level blocklet index. Block index is nothing but contain a blocklet index node for each blocklet stored in the file. Each block index node contains a start-ending key of the MDK index, and also min-max value of each columns. So at runtime, this information we will build an in-memory representation of the blocklet index, a B-tree index for efficient filtering. And we are finding it has been very optimal to be able to do a much better job to filter out blocklet within a file in a way which we can safely exclude more blocklet scans compared to only a min-max index alone. Based on the index information we stored in the footer, we talk about we can build a file level index, a local B-tree index to filter a blocklet within a file. If we combine the file footer information and extract this information, we are able to build a higher level of indexes, what we call table level index, which is a global B-tree index for us to be able to efficiently filter carbon files at Spark driver. So we have two types of B-tree index at different levels. One is filtering on carbon files on the driver side, and on the executor side, we have been able to filter out blocklet within a file to do a much more better, efficient scan to be able to safely skip some file scans compared to other file format. We're going to talk in more detail about how to leverage all this different level of index support in the Spark integration session. Beyond B-tree index, we also support a column chunk level inverted index where the data are sorted within a column chunk. And this is generally applied to very low cardinality columns so that we can achieve a better compression ratio as well as we can do a massive quick binary search on the column chunk data when we are applying a filter expression. We will have an example to showcase how we leverage all three different types of indexes later on. So now let's move on to take a look at the carbon data table. So from a very high level, carbon data table, you can define a carbon data table through a create table statement. When you define the table, you are going to specify the MDK index. What are the set of columns you're going to pick to form the index keys? Then when you load the data, populate the table, you are going to first sort the data along the MDK indexes, and then you're going to store the carbon data file under a segment. What we call a segment is a directory under the table root path directory to create a new segment for each data load. So on top of that, we also have indexes built by extracting file footer information within the segment. For low cardinality columns, we also perform global dictionary encoding. So for global dictionaries, we are going to keep it in the metadata folder of the table. So as you can see, a carbon table is formed with a segment directory, and for any subsequent data loading, the same process will repeat for any subsequent load. A new segment will be created to hold the data as well as index for this segment, as well as if we find any new values, we're going to append this value to update the dictionary. So as you can see, here is a layout. Here is demonstrate the layout of a carbon table on disk. So we have segment folders as well as metadata folders. At the driver side, we're going to load the indexes into memory to facilitate the query processing. Besides data load, we also support more fine-grained mutation on carbon data files. So for delete statement, which is since carbon data files are immutable files, they stored on HDFS. So instead of overwriting the file, we introduce the delete delta. Basically, it's a bitmap file. Basically, just mark what are the rows are deleted. Then during query time, you are going to first scan the base table, the base files. After that, you're going to consult the bitmap file to exclude the rows which are deleted, no longer exist. Besides delete, we also support update operation. Update is nothing but translate into a delete followed by an insert. So for delete delta, for delete operation, we do the same for a delete statement. The insert part, we are going to dump the insert delta into a regular data files. And then we are going to build a new index for those new files as well. So as you can see, it's very possible after the delete or update operations, you might generate a lot of small files. And also, if you have a lot of small data load process, you are going to generate a lot of small files on the disk. So this is generally not a good idea on HDFS. So we provide a compaction facility, a tool, to compact small files into big files and consolidate all the delta files with the base files to form a big files. Or we can also do a major compaction. In that case, we are merging a JSON segment, small segment, into a bigger segment. So in that case, we are reorganizing the data and for better clustering on the MBK index for more efficient filtering. As we support, because we want to support concurrent query, read, and also load and compaction at the same time. So we also have a component to manage the segment. So internally, we actually leveraging Zookeeper to manage the segment state. Basically, what we are trying to achieve is to make sure the write operation are only the new segment directory are only available and visible to read only when the load or compaction is complete and successful. Next, we're going to talk in great detail about integration with Spark. Jacky is going to take over.
So let's talk about how we integrate Carbondata with the Apache Spark. Currently, Carbondata is integrated with Spark starting from version 1.5 up to 2.1. User can use SQL at the data frame API to interact with Carbondata. User can load data into Carbon table and query visit with the query optimization enable provided by Carbondata, and also can update and delete and do some compaction, data management on the table. So there were Carbondata is a file format on top of HDFS. So we provide input format, output format, which work with any processing engine compatible with MapReduce API. So Hadoop MapReduce Spark link, you can use it to read and write Carbondata with the file format API. And we did more to integrate with the Spark SQL. Besides the file format, we also integrate the index and the dictionary part into the Spark SQL optimizer. This is how we do it. So we leverage the Catalyst framework and to plug in the Carbondata as a data source into it. Basically, there are three parts of the plugin code. The first part is the syntax, because we support more syntax than the native Spark. So we have new parser which can interpret the update, delete statement. Second part is the optimization rule. This optimization rule is, one of them is so-called lazy decode. So this is to accelerate the aggregation query by leveraging the global dictionary. Third one is about the execution. We write some RDD specific to Carbon, like scan RDD, which will leverage the multi-level index in the Carbondata. So let's take an example of how Spark leverage the index. For example, for this query, select C column 3, column 4, and there's a predicate on C2 equal to Boston. So when this query comes to Spark driver will leverage the table level index to prune the files. So in this example, you can see there are 4 files in the HDFS. So there are 4 leaf nodes in the table level index. Suppose there are only 2 files matching, containing the record which matching this predicate. So only 2 leaf nodes is hit. So 2 tasks will send to the executors. In the executor side, we'll run the scanner in the Carbondata. In the scanner, we are not trying to scan all the data in the file. Instead, again, we will build this file level index to further pruning the broadleaf. So suppose only one of the broadleaf is hit in each one of the tasks. Then the scanner will open this broadleaf file and then try to read the C2, which is the filter column, into memory and decompress it into memory. Then apply the binary search to search the Boston on this C2 column. If there are match rows, then we will decompress the other projection columns. If there's no match row, then we'll skip this into next broadleaf. So this is basically how we leverage the index to reduce the amount of I/O. Next technique is we call lazy decoding. By doing this, we can reduce the amount of data in shuffling and accelerate the aggregation. So take, for example, this query, do a group by on C3 and do a sum on C2. Before applying this technique, the orange plan, you can see there's a scan to decode both C2 and C3, and then do a partial aggregation and a final aggregation in the stage 2. After applying this optimization rule, scan only will decode the C2 because he will do the partial aggregate and the final aggregate on the encoded value of C3, which will be the integer value. So this aggregation and the shuffle will be much more efficient. Then finally, there's this operator to decode the C3 back to the original value, which is a string value. Let's see how we use this Carbondata. So this is the Hive standard syntax. You can create table and load data into Carbondata. You can do the same by using data frame API. You can read the Carbondata table by using SQL and data frame also. And this is how you do the update and delete. So we provide I provide 3 examples here. First one is to modify one column. and filtering the product equal to phone. Second one is we update two columns in the table 1 using the join result of these two tables. So you can perform a subquery and then update the first table. Third one is to delete all the records which have the customer ID equal to 123. Let's see some performance results we have done in our test. So there are 3 of them. First one is a standard TPCH benchmark. The scale factor is 300 GB. Next one is we have done some tests in the production deployment. And third one is we can see Carbondata, how it can scale for large data set, which up to 1,000 billion rows, which is more than 100 TB. So we compared using the Parquet and the Carbondata. The Parquet data is partitioned by time column, which is the first column. And for Carbondata, the MDK key index is built on the C1 to C10, so 10 columns. The compute engine is using Spark 2.1. So among the 22 test cases in the TPCH, if we pick those cases which have the bit scan, actually they perform very closely. Some query carbon scan is faster, some query Parquet is faster, but overall they are very similar. But if you look at the query which has the filter on the fact table before the join, so Carbon can leverage its multi-level index to prune the files and prune the block list, so less I/O will be performed. In that case, Carbon can perform up to 20 times faster. Talking about the loading performance and the compression ratio, because Carbondata, when loading, it needs to sort the record, so it takes time. So it's fair that Carbon loading speed is like half of the Parquet loading speed. And the compression ratio is similar. And this test is performed on a production data set. We tried a different combination of filter columns then to see what's the response time of the Carbondata. You can see because all this column is within the MDK range in the Carbondata when you create the table, so this performance is quite good comparing to Parquet. And why is this? Because in the driver side, Spark is able to prune the file so that less task is sent to executor. You can see the number of tasks for Carbondata is less than the Parquet task. This is for the aggregate query example. In this query, there's no filter and group by one C file, which is a dictionary encoded column. You can see the execution time, Carbondata is half of the Parquet. And if you open up the stage execution time, both the stage 1 and the stage 2 for the partial aggregate and the final aggregate, Carbondata stage is less time than Parquet stage. This is for the large data set test. This is tested in a 17 node cluster, which is 1,000 billion row. So you can see as the number of records increase, the response time is not increased so much. So we can say that the index helped this I/O bound query a lot. But if the query is a CPU bound, like this Q3, it is full scan aggregation query. So all the records give to Spark to do the aggregation. So you can see that Spark also scale very well for the computation. So let's see the roadmap. First point we'll do in the future is to further improve on the loading and the compression of Carbondata. And secondly, as now more and more data is come as a streaming manner, so we want to work on introduce the row-based format to support the streaming ingest. Since Carbondata already have the compression facility, so we can use the compression process to convert the raw data to columnar data during the compression. And thirdly, because we are new format in the ecosystem, so we want to integrate with more processing engine in the Hadoop ecosystem. And as a new Apache incubator project, we love feedbacks. If you're interested in Carbondata, please check it out. We will answer questions in this community, so please check it out. So thank you. Yeah.